Hello everyone, in this lecture we'll look at Pascal's Triangle. So what is Pascal's Triangle? Well, this is Pascal's Triangle. This is not limited to these numbers. We have more numbers underneath this row, but this is what I can fit in the screen. So what is this thing? What is this triangle? Well, you may look at it and say that there are a lot of random numbers, but actually there aren't any random number. Every number that is right here, every number that we have right here is made by a process that is very logical. So let's say we want to create the Pascal's triangle. How do we do it? Well, first we start with 1. We will put 1 on the top of the pyramid, and any number that we want to produce after that is just the sum of the number on top of it plus the one that is beside it. So here we have 1, and the number that is on top of here, the number on top of 1 is 0 plus the one beside it is 1, so we get 1 right here. Just like here we have 1, the number on top of it is 1 plus the one beside it is 0, so we get 1 right here. 2 is the result of the number on top of it, which is 1 plus the one beside it, so 1 plus 1 is 2. 4, for example, is the result of the number on top of it, which is 1 plus the one beside it, which is 3, so 1 plus 3 is 4. 20 is the result of the number on top of it, which is 10 plus the one beside it, plus 10. 10 plus 10 is 20. 28 is the result of the number on top of it, which is 7 plus the one beside it, 21, so 21 plus 7 is 28. So every number that you see right here in the Pascal's triangle is the result of the number on top of it plus the one beside it, and we start with having 1 on top of everything. So why is this triangle important, and how is it related to counting or combinatorics? Well, I'll show you how it is related to combinatorics, but first let me show you some beautiful patterns that we can see in Pascal's triangle. The first thing is this triangle is symmetric about the y-axis. So every number that we have on this side, we have exactly the same amount of value on the other side. So for example, we have 1 right here, we have 1 right here, we have 5 right here and 5 right here, we have 10 right here, we have 10 right here. And you may say, well, what about the ones that are in the middle? Well, let's see. 20 can be divided into 2. 10 right here, 10 right here. So 10 to the right side and 10 to the left side. The same goes to 70, the same goes to 252. So all of these numbers that are in the middle can be divided into 2, one of them to the right side and one of them to the left side. So as you can see, we have perfect symmetry about the y-axis. Every value or every number that we have right here on the right side, we have it on the left side. So this is something beautiful about Pascal's triangle. Beside that, these, as you can see, this red line goes on top of all the counting numbers. So we have 1, 2, 3, 4, 5, 6, 7, 8. These are all the natural numbers till infinity. So in Pascal's triangle, we have the counting numbers on this side. As you can see, 1, 2, 3, 4, 5, 6, 7. And on this side, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and keep going. So we have counting numbers as a pattern in Pascal's triangle. Beside that, we have triangular numbers in Pascal's triangle. How is that? Well, as you can see in these numbers, 1, 3, 6, 10, 15, 21, 28, these are triangular numbers. What do I mean by triangular numbers? Well, imagine we have 3 balls, or imagine we have 3 dots, 1, 2, 3. If you put 1 on top and 1 right here and 1 right here, you can create a triangle by 3 dots. Again, you can create a triangle by 6 dots. You can have 1 on top, 2 on bottom, and 3 underneath. Just like here, we have 1, 2, 3, 4, 5, 6. We have 6 points. We can create a triangle out of them. Again, by 10 we can create a triangle, by 15 we can create a triangle, and by 21, 28, 36, 45, and so on, we can create triangles. So these are called triangular numbers. So this line right here is triangular numbers. This line right here is the counting numbers. And if you add all the numbers on each row, you'll get another beautiful pattern. So here it's 1, here is 1 plus 1 is 2, 1 plus 2 plus 1 is 4, 1 plus 3 plus 3 plus 1 is 8, and so on. So if you add all the numbers that are in a row, you'll get a number. So you'll get 1, 2, 4, 8, 16, 32, 64, and 128, and so on. So if you look at it like this, these numbers right here, the one in yellow, what kind of pattern do they make? Well, actually they are the powers of 2. So here, this is 2 to the power of 0, this is 2 to the power of 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, and 2 to the 7, and so on. So if you add all the numbers in a row, you'll get the powers of 2, because 1 plus 1 is 2, and 2 is just equals to the power of 1. 1 plus 3 plus 3 plus 1 is 8, and 8 is just 2 to the power of 3, and so on. So as you can see, we can have a lot of beautiful patterns in Pascal's triangle. All these patterns, like the power of 2 and all the counting numbers and triangular numbers and many more, we can have in Pascal's triangle. However, I want to show you how we can use Pascal's triangle in order to count combinations and in order to count how many ways we can have different elements together. So for that, let me give an example. Let's say we have this example that says if you toss a coin 2 times, there's only one combination that will give you 2 heads, but there are 2 that will give you 1 head and 1 tail and 1 for all tails. So if I have a coin and I toss it twice, there's only one combination that will give me heads and heads and tails and tails. Let's say I'll toss it once and I'll get heads, and I'll toss it another time, I'll get heads. So if both those tosses are heads, then I'll get both heads. There's only one combination. The same goes for all tails. However, there's 2 combinations that will give us heads and tails. So if I toss it once, I'll get a head, and if I toss it twice, I'll get a tail. Or if I toss it the first time, I'll get tails, and the second time heads. So there are 2 combinations that will give us heads and tail, one combination that will get us heads, and one combination that will get us tail. So it is 1, 2, 1. So can we find this 1, 2, 1 in Pascal's triangle? Well, actually, yes, we do, and I highlighted it in red. We can have 1, 2, 1. So this is the combination that we get when we have a coin and we toss it twice. There's only one combination that we get heads, one combination that we get tails, and 2 combinations that will give us heads and tails, and it is 1, 2, 1. You can tweak the example and change it that in a way that it will give us 1, 3, 3, 1. So if we toss the coin 3 times, there's only one combination that will give us the heads, meaning H, 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 but there are 3 that will give us 2 heads and 1 tail, and 3 that will give us 1 head and 2 tails, and 1 for all tails. So it will be 1, 3, 3, 1. So 1 for all tails, 1 for all heads, 3 for 2 heads and 1 tail, and 3 for 2 tails and 1 head. So it will be 1, 3, 3, 1. So as you can see, the patterns that we have in Pascal's triangle they are actually ways of combination. They are actually permutations without repetition. So the rule that we use, for example, in order to solve this problem, how many ways we can get 3 pool balls out of the 16, we usually use this rule, which is n factorial over r factorial times n minus r factorial. We can use Pascal's triangle in order to solve this problem without using this rule. So the answer to this question is 16 factorial over 3 factorial times 13 factorial, which is 560 ways. So how many ways we can get 3 pool balls out of the 16? It is 560 ways, and this is a permutation problem with no repetition. Let's see if we can use the Pascal's triangle in order to get this number 560 when we have 3 pool balls out of the 16. Well, we can do it if we substitute the n for the steps going vertically and r for the steps going horizontally. So we have n factorial over r factorial times n minus r factorial. If we substitute n for the steps going vertically and r for the steps going horizontally, we will get the same result as solving the problem by the rule. But keep in mind, the top row and the first place is always 0. So here, right here, when we have this one right here, this is the 0th row. It's not the first row, it's the 0th row. And here, these ones are the 0th place. So we have the 0th row, the first row, the second row, third row. We don't have the first row on top, we have the 0th. And here we have the 0th place and the first place, the second place, the third place. So we have 16 balls and we take 3 out randomly. So let's see, we have 16 balls, so we will substitute the 16 by the steps going vertically. So it will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. And we have 3 balls chosen randomly. So this is 0, 1, 2, and 3. And ta-da! We got 560 as the answer to this problem. So as you can see, we can use Pascal's triangle in order to solve problems of permutation, the ones that do not involve repetition. And we use it instead of the rule that says n factorial over r factorial times n minus r factorial. So it is this problem, it is this rule right here, is n factorial over r factorial times n minus r factorial. So we can use the same rule in order to see the values of the places in Pascal's triangle. So if someone says, so what is the value in the third row, third element, we can use this rule in order to find that value. So how do we do it? Well, we use the n steps going vertically and r steps going horizontally. So let me give you an example. Let's say we have row 5 term 3 is 10. So row 5 is 0, 1, 2, 3, 4, 5, 0, 1, 2, 3. So row 5 term 3 is 10. Let's see if we can use this rule in order to find this value, which is 10. So we basically, our n is 5 and our r is 3, so it will be 5 factorial over 3 factorial times 2 factorial. 5 factorial is 120, 3 factorial times 2 factorial is 12, so it will be 120 over 12, which gives us 10. You can do the math by yourself, so it is 10. So we can use this rule in order to find the values that are in the Pascal's triangle, or we can use Pascal's triangle in order to find this value, in order to find permutations and combinations of things and elements that can be arranged together, as we saw it in the 16 balls, or as we saw it in the choosing 3 balls out of the 16, which gives us 560. So Pascal's triangle is a very neat concept that was invented by Pascal, and despite having many properties and many patterns in it, it's a way in order to find combinations and arrangements of things, especially combinations. Instead of using n factorial over r factorial times n minus r factorial, we can use Pascal's triangle in order to find the value, as I showed you in the examples. So this is it about Pascal's triangle.